Assalamualaikum and good day everyone. We are group 7. So today we'll be presenting on the solution to ordinary differential equation. From question 1, first step was to form a second order differential equation using Newton's second law. As you can see, by considering the forces acting on a mass spring damper system, the spring force, damping force and applied force. After we got this equation, we set in a constant, this simplified to the general form. From this, we derive the characteristic equation, which gives us the roots using the quadratic formula. For the solution to ODE, first the undetermined case where b squared less than omega squared. Here the roots of our characteristic equation are complex. This leads to the oscillatory solution that gradually decay. Next, for the undated case, we have b equal to 0. This means they are not damping and our root become purely imaginary. The solution is a simple harmonic motion with constant amplitude. Other than that, in the theoretically dampened case, b squared equal to omega squared. The roots are real and equal, resulting in solution that returns to equilibrium as quickly as possible without oscillating. Lastly, for the overdamped case, b squared more than omega squared. Here, the roots are real and distant. The solution shows a slow return to equilibrium without oscillating. Each of these cases provides a distinct behavior for the oscillating system.
So for the undamped oscillation, by using the formula just now derived, and we substitute b equal to 0 and omega equal to 3.274, and the bit A and bit B is substitute any constant, then you will get this graph from the decimals, which the amplitude actually does not change over time. So this one actually is the simple harmonic oscillation. However, for the underdamped oscillation, by using the formula just now for the underdamped oscillation, where omega greater than b, you will get this graph, which the amplitude actually is decreased over time, but the frequency actually is not changed significantly over time. So this one is the underdamped oscillation, where the amplitude drop showing the damping.
This is the critical damp case equation, which is omega equals to the b. The graph for the critical damp case, just like overdamped case, there is no oscillation, but the system returns to zero much faster. This faster possible setting without overshooting. This is the equation for the overdamped case. The omega is smaller than the b, and we put the constant into the equation. We can see that the displacement decreased smoothly over the time without any oscillation. However, it took longer to reach zero compared to the critical damp.
Here is a video demonstration of the damping system. So when the system is undamped, B is equal to 0. So the graph will forever oscillates indefinitely. For this, L less than square root 4 mk, the system is underdamped. So the graph will still oscillate, but the amplitude will gradually decrease. Next, when the system is critically damped, in which L equals to square root 4 mk, there will be no oscillations, but the graph will return to equilibrium the fastest. And when the system is overdamped, in which L is more than square root 4 mk, the system will also not oscillate, but it will return to equilibrium much slower.
Based on the observation, the damping process that are suitable for automobile is critically damped. Since critically damped system provide the optimal balance, it returns to equilibrium quickly and smoothly without any oscillation. This ensures a comfortable ride while maintaining good handling and control. Critically damped is generally the best for automobile suspension systems. This is because it allows the vehicles to return to a stable state or in equilibrium as quickly as possible after encountering a bump or uneven surface without oscillating or bouncing excessively. Therefore, while all four damping types, underdamped, undamped, critically damped, and overdamped, have their place in engineering, critically damping is the most preferred choice for automobile suspension system due to its ability to provide a comfortable and controlled ride.